Welcome to inverse functions. Now I know you did them in whatever math class you've had before, but did you understand what they kind of looked like? So for an inverse, let me do it the other way. For a normal function, we're given a value of x, mapped it from using the function we're given to give us our value of y. Inverse is just going to use the opposite. What it's going to mean is it's going to give the y value, and using the inverse, we should get back to the original x value that we were given. That's the inverse. Now, the interesting part is using the inverse function from x to y is defined that you have one path back and forth. So that's why it has to be a bijection function, both one-to-one and onto, because we want to have, number one, every one of those values in the codomain being used. That's number one. Number two, every value in the codomain can map to literally just one value from the domain. So here you're going to see the mapping of f of x. We get all our values and map it to our y. And then when we use our inverse, notice we're using y to then map back to our original set of, well, this time it's going to be a set of z, but that's going to be our original domain set that we used. Here's example number one, where f is a function from, notice a very explicit mapping everything out. Notice already, by the way, there's a dead giveaway here because it doesn't have the same number of values in the codomain or range than our domain. Number two is the overall layout, but let me get everything. There's the mapping that we have, f of 1 to b and 3. Is f invertible? Remember, it needs to be both one-to-one and onto. Now, I can knock that right off the bat. This is a problem. We should not have anything that we can't reach in the codomain. So that means the range is going to be smaller than the overall codomain. That's a stop right there. So we know that's not going to be a bijection because it's not an onto, so therefore it's not going to be invertible, because invertible needs both onto and one-to-one. In example number two, it's a word problem. Not a big deal. We could still draw this out, but still, we got to do some of the work that we've got already labeled here. So just a heads up. So let f is an integer of x domain, the y domain is going to be integers such that f of x is x plus 3. So again, I went ahead and put up our two definitions that we have to have it be one-to-one and onto, just to make sure that we're good here. And again, we're using integers too, so we got to be very careful about that as well. Now, if we do a mapping of one-to-one here, we're going to basically figure out that, hey, these are going to be the same values. It's maps to only one value in the domain given a value of y. So notice the values for a and b are the same, but we're given the same y value. There's no difference between the two. So yes, there's no possibility of changing that. It's just a one-to-one. For the onto portion, which is a little bit more interesting, but still okay, is that I try to give it basically a sampling of different numbers here of y values, and that's going to map to our domain of different values here. And notice it can go negatives, it can go positives, it can go anywhere that we want. We really should try to do a 0 in here as well. But yes, for an onto, every element in the codomain is going to map to at least one element in the domain. So we're in good shape when it comes to onto as well. So both of these are a yes, so then I can move on to what's my inverse going to be. Now when we do this, it's actually very simple, thankfully. All we do is replace the f of x with x and replace x with the inversion of, or inverse of, f. So notice this was the original equation. I did exactly what the instructions are telling me here. So I go ahead and try to move f of x into one side, and basically I do that, I just flip it sides here on the last line here to make it easier for us to read. So f of x is going to be x minus 3, which frankly, hey, that should make sense. So we're in good shape.